When we discussed rate laws, one of the things I said that makes it much, much easier to determine what the order of a reactant is depends on when the other reactant concentration doesn't change. Okay. However, sometimes when you're doing rate law problems, it gets a little bit more complicated because, for example, if you look down here at this example, you'll notice that there's never a time where the S2082- stays constant. And so that's going to kind of throw a wrench into our problem here when we're trying to figure out what the order is with respect to I minus. So when you do this, you must first find the order of the reactant where it does stay the same. So for example, here we see that I minus stays the same for the first two trials. So that's going to help us to figure out what the order of S208 is. Okay? Then we have to take that into account. We have to take that order into account to determine the order of the other reactant. And I'll show you what I mean by that. Okay, so here's an example here. We see the reaction. It's got two reactants. So the first thing we want to do is, again, determine the order with respect to each reactant and write the rate law. So the first thing we're going to do, again, we're trying to find, again, two trials where they stay the same. So in trials 1 and 2, the concentration of I minus stays the same. And the concentration of S2O82 minus goes up by a factor of, and whenever you're not sure, if you're not sure how much it's going up by, you can simply use a calculator, especially if it's free response. Just take 0.027 and divide 0.018, and you should find that it is increasing by a factor of 1.5. That especially comes into play, especially when you have exponents, numbers in scientific notation that have different numbers up in the different exponent values. And sometimes you're not sure. Well, always just take the second one, divide by the first one, and then see how much it changes. So even here, if you're not sure how much different that is, take 3.9 times 10 to the minus 6 and divide it by 2.10 to the minus 6. And then you should also find that it's also 1.5. Okay, so if S208 goes up by 1.5, the rate goes up by 1.5, we know that that S208 is therefore first order. Okay, so we've got that out of the way. Now the tricky part comes, and this is the real important part. If you're not paying attention, start paying attention, is we have to figure out what is happening with I minus. But again, there's never a time where S208 minus stays the same. So we're trying to find an experiment where I minus changes by something that's relatively obvious, but then also we can calculate what S2082 minus is doing. Okay, for example, if we look at there's lots of different ways you can do this, guys. But one way is to look at trials 1 and 3. And in trials 1 and 3, S2082 minus doubles. So without even considering I minus, what is this rate right here going to do when S2082 minus doubles? Well, since we know that it's first order, we know that if S2082 minus doubles, then the rate is also going to double. So before we even try to figure out what I minus is going to do, we're going to say, well, because of the S2082 minus, we know that this rate is going to go from 2.6 to 5.2 times 10 to the minus 6, because we already know that S2082 minus is first order based on what we already did. Now that we have this new rate based on the fact that S2082 minus doubled, now we can look at I minus. What does I minus do in those same two experiments? Again, if you're not sure, then divide them. Take 0.054 and divide by 0.036. Again, it should equal 1.5. Okay? Now, do the same thing here. Take this 7.8 times 10 to the minus 6 and divide by 5.2 times 10 to the minus 6. Or, if you can figure it out in your head, 5.2 times 1.5 equals 7.8. So therefore, the rate, after we take into account S2082 minus, is also going up by a factor of 1.5. But obviously, if you just look here, guys, if you're just looking at, well, it's tripling, right? From 2.6 to 7.8, it's going up by a factor of 3. Well, again, that's because you're not taking into account the change that S2082 minus has. And if this goes up, if the concentration goes up by 1.5 and the rate goes up by a factor of 3, 1.5 raised to what power equals 3? There really isn't one. I mean, there is. Again, what would you do is you would go x times the log of 1.5 equals the log of 3, and then in your calculator, you'd go log of 3 divided by the log of 1.5. I got to put parentheses around that 3. Insert divided by the log of 1.5, and it's some weird 2.71, okay? You're not going to have an order that's 2.71, okay? So, after taking into account S2O82 minus, this goes up by 1.5. This went up to 5.2 because of the S2O82 minus, and then it went up by 1.5, just like I minus did. Therefore, they are both first order. Okay, so the order with respect to each reactant is first order, and we say they're first order, and then we explain why. Because in trials 1 and 2, I minus stays the same. S2O82 minus goes up by 1.5, so does the rate. Okay, and then we explain, again, same logic, in trials 1 and 3. Let's go through this again. In trials 1 and 3, S2O82 minus goes up by a factor of 2, so the rate will go up by a factor of 2 because it's first order. So there's our 5.2 times 10 to the minus 6. Okay, and then in those same 2 trials, I minus goes up by a factor of 1.5, and then so does the rate by another 1.5. So I minus is also first order. And yes, you want to write all of that. Make sure the grader knows that you know what you're talking about. If you just say 1.5, and in this case I should say, they're not asking you to explain, but you certainly should. Okay, so then write the rate law. The rate is equal to K times the concentration of S2O82 minus times the concentration of I minus. What is the value of the rate constant? Again, let's just take, I'll just take the first trial. You don't have to, you can take any trial. Molarity per second is going to equal K times the concentration of S2O82 minus 0.018 molar times 0.036 molar. And then I'm going to solve for my unknown. So I'm going to take 2.6 times 10 to the minus 6. I'm going to divide by 0.018 molar. I'm going to divide by 0.036 molar. And I get 4.01. Actually, there's only 2 significant figures. So 4.0 times 10 to the minus 3. And then in terms of units, this molarity and one of these molarities are going to cancel. So you're going to have the molarity on the bottom, so molarity to the minus 1, and then seconds to the minus 1. Okay, now they're saying, so now we're changing it up a little bit. What is the rate of disappearance when now you've got different concentrations? So again, the rate of the reaction can be measured in how fast the reactants disappear or how fast the products appear. So now that we have the rate constant, now they can give us different concentrations, and we can still find the rate. So the rate is going to equal the rate constant, 4.0 times 10 to the minus 3, molarity to the minus 1 seconds to the minus 1, times the concentration of S2O82 minus, times the concentration of I minus, and then again, notice this molarity to the minus 1, and one of those molarities will cancel, so you'll be left with molarity per second. So we'll take that rate constant, we'll multiply it by 0.015, we'll multiply it by 0.040, and we get a rate of 2.4 times 10 to the minus 6 molarity per second. And again, this is another one where they're not really going to care about units because the rate is always in concentration over time. But here, they absolutely are going to care about this. All right, so in this case, so now we saw once you know the rate constant, they can now give you different concentrations that are not going to be in this data table, and then you can still calculate the rate, okay? Now, sometimes when you solve rate problems like these, the rate, instead of them just saying the initial rate, well, what is that the rate of? Is that the rate of disappearance of S2082 minus? Is it the rate of disappearance of this? It might be, the rate might be the appearance of SO42 minus or the appearance of I3 minus. Okay, so many times when they give you the rate, they're not going to say just the rate. They're going to say the rate is in terms of the disappearance of one of the reactants or the rate of the appearance of another. Okay, when this occurs, you may be asked to find the rate of disappearance or appearance of another reactant or product in the reaction. So to do this, you simply use, now here's where you use the stoichiometry of the balanced equation to find the rate of the reactant or product in question. Now be very careful there, okay, because you can't find the order of the reactants. But once you know the rate of disappearance or appearance of one of the reactants or products, you then can use the balanced equation. So consider this reaction. 2 NOCLs makes 2 NOs and a Cl2. Okay, based on this balanced equation, we can see that 2 moles of NOCl have to disappear for every 2 moles of NO that are formed and for every 1 mole of Cl2 that's formed. Therefore, the rate of disappearance of NOCl, the rate at which this disappears, must equal the rate at which NO must appear, because for every 2 of those that disappear, 2 of those NOs are going to appear. But for every 2 of those NOCLs that disappear, only 1 Cl2 is going to appear. So that means that the rate of appearance of Cl2 is going to be half the rate that NOCl is disappearing. Okay, so example 2. Using example 1 above, determine the rate of disappearance of I minus in experiment 2. Okay, so in experiment 2, we can see that the rate, now here they do say it. A lot of times they'll have it in the data table, but it says at a particular temperature, the rate of disappearance of S2082 minus. So that's this rate. The rate they're referring to is the rate of disappearance of S208 minus, 2 minus, excuse me. Okay, so we want to determine in experiment 2, or the second trial, what is the rate of disappearance of I minus? So watch how I do this. So first of all, I need the rate. So in trial 2, the rate was 3.9 times 10 to the minus 6, and that's the concentration, again, of S2082 minus and how it's changing. Okay, so we're going to say 3.9 times 10 to the minus 6. That's moles of S2082 minus disappearing per liter, and that part really doesn't matter because all we're going to do here is we're just going to do stoichiometry. So based on that balanced equation, we know that 1 mole of S208 is going to react with 3 moles of I minus. And what that tells us is that the rate of disappearance of I minus is going to be 3 times faster than the rate of disappearance of S2082 minus. And we can show that mathematically. We can say for every 1 mole of S2082 minus, 3 moles of I minus are going to form. Okay, and so the moles of S208 cancel. We just take that number, 3.9 times 10 to the minus 6, and we multiply it by 3, and we get 1.2 or 1.17 times 10 to the minus 5th molarity per second. Okay, and that's how fast the I minus is going to disappear. All right, let's look at one more example. An unknown gas D reacts with fluorine gas to form the compound DF4 as represented by the following equation. A series of experimental trials were performed at 600 degrees to determine the rate law expression for the reaction. Data from the trials are shown below. What is the initial rate of disappearance of F2 in trial 1? Justify your answer. So right away, they're telling you the rate of appearance of DF4 is, again, at 3 different trials. So we're talking about in trial 1. So here's one where when you see a rate law problem, you instantly want to start looking at, okay, this one doubles. What does this do? This one doubles. These stay. You know, you want to start looking at that. Okay, but once you know the rate of one thing, so this is the rate of appearance of DF4. So we're talking about trial 1. So when they're talking about a specific trial, you can't compare one trial with another trial. You only can talk about trial 1. So in trial 1, the rate of appearance of DF4 is 2.5 times 10 to the minus second. So 2.50 times 10 to the minus second. Now notice in this case they're not using molarity, they're using torr, which is a unit of pressure. Okay, and that's fine. They're just trying to throw you off with that. Don't let them. Torr per minute. Okay, and now from that balanced equation, even though it's not moles, we can still use the stoichiometry of the balanced equation here. We can say that for every 1 mole of DF4 that's formed, and then they're asking about F2. There are 2 moles of F2 that get used. So 2.5 times 10 to the minus second is 5 times 10 to the minus second torr per minute. Okay, and wait a minute, but this is moles and torr don't cancel. Don't think too much into this, okay? Anytime you know the rate of appearance or disappearance of one component of this reaction, you can always, whether it's in torr or moles per liter, whatever, or atmospheres, anything, you can use stoichiometry to convert from one to something else. Okay, don't try to use a rate law in a problem like this. In part B, where it now says determine the order of each reactant, now absolutely yes, you have to use the data to figure out the order. Okay, and again, hopefully now this is getting a little bit easier. So in trials 1 and 2, the pressure of D doubles, the rate also doubles, therefore D is first order. Okay, and then in comparing, it looks like comparing, again, I'm trying to find 2 where D stays the same. In trials 1 and 3, D stays the same. F2 doubles, goes up by a factor of 2, and then the rate goes up by a factor of 4. Okay, from 2.5 to 10. And they could have made this more difficult. They could have said 1 times 10 to the minus 1 to be correct in terms of scientific notation, but they were trying to make this question easier. So they did go all the way up to 10, just so it would be easier for you to see that it's going up by a factor of 4. So F2 goes up by a factor of 2. This goes up by a factor of 4. Therefore, F2 is absolutely second order. Okay, and then you would need to justify that. I just don't want to waste all your time here. I know you know how to do that now. Okay, and then write the rate law. Great, easy. Rate equals K times the concentration of D times the concentration of F2. And obviously that is squared because it is second order. And then calculate the value of the rate constant. So again, just choose, and I'll choose a different one this time just to show you that it doesn't matter. I'll use trial 2 this time. So the rate is 5 times 10 to the minus second. So 5.00 times 10 to the minus second. Molarity, oh no, it's torr, right? Torr per minute, that's right. Just to kind of, again, try to mess with you. Torr per minute, this will be a good one actually, is equal to K. Now we need the pressure or the concentration of D, which is, again, in trial 2, it's 6,000, and in F2, it's 3,000. So we're going to have 6,000, and that's in torr. Make sure you're consistent on your units here. So 6,000 torr times 3,000 torr, and that is, of course, squared because it's second order. So I'm going to take, this is going to be a pretty small number, 5 times 10 to the minus second divided by 6,000 divided by 3,000 squared. Don't forget to square that. Okay, and yeah, that's a pretty small number. So K is going to equal, and again, the order that you do it, it doesn't matter, 9.26 times 10 to the minus 13th. Now let's figure out our units here. This torr and that torr will cancel. So we've got a torr squared. So on the bottom, we're going to have torr to the minus 2 and then minutes to the minus 1. Okay, and now we have the rate constant, and now they're going to change the conditions for us. Now they say, all right, now we're going to change the pressures to this. What's the rate? Okay, and so again, the rate is going to equal that rate constant, 9.26 times 10 to the minus 13th. Again, torr to the minus 2, minutes to the minus 1. times the pressure of D is 4,200 torr, and F2 is 6,400 torr. And again, don't forget to square it. So I've still got that rate constant on my calculator screen. So I'm just going to multiply by 4,200 and multiply by 6,400 squared. And that equals, doesn't need to be in scientific notation, that rate is going to equal 0.16. And again, that's going to cancel with those torr squared. So you're going to be left with torr per minute, or torr minutes to the minus 1.